and the Hasso-Plattner Institute. So, oh no, my remote doesn't work. So, let's start off with an example. Here's a nice idiomatic definition of the dot product function in Racket. It's the kind of code we would really like to write in Racket. Unfortunately, it's not really the code we want to run. This example ends up running pretty slowly. So as one possible option, we can hand this off to our local Racket guru, and he'll come back with some code that looks something like this. Our code has now been manually specialized to unsafe, type-specialized variants of all the arithmetic operations. Our nice loop construct has been rewritten to manual recursion. But we're now 10 times faster, so maybe this was worth it in this case. Now, since we're in Racket, we could also go a slightly different direction and try to implement a safer dot product using Racket's contract library. And we'll get something like this, where we use a contract to enforce that we're receiving a pair of floating point numbers, and we'll produce a floating point number. And then we just wrap our original definition in that. Unfortunately, this imposes extra overhead still. We're now about 2.5 times slower for what is adding effectively just a type annotation. So we developed Picket to try to improve some of these cases. Particularly, we want to reduce the need to manually do this type specialization and the need to remove safety constructs like contracts merely to get performance. And so this here at the bottom is the runtimes for the various dot product examples under Picket. As you can see, not only are they significantly faster in all three cases, but the variation in performance between the fastest and slowest version is only about 25%, as opposed to 2,500% in the under Racket. So the general idea here is we apply modern JIT compilation techniques that have proven effective in languages like JavaScript and Lua, and apply them to a functional language like Racket. And in particular, we make use of the R-Python project, which came out of the development of PyPy. R-Python is a language and framework for developing high-performance dynamic language VMs, most notable for its inclusion of a language-agnostic JIT compiler, which we make use of. And so our major challenges when making use of R-Python to implement something like Racket is we need to identify loops in our Racket source code, which is the unit of compilation used by the R-Python JIT compiler. And finally, we need to expose enough information to the JIT compiler so that it can perform this manual specialization for us and hopefully expose enough information about our contract library so that it can remove some of that overhead. So a little on the high-level design, rather than go through the long, tedious process of implementing a complicated bytecode VM, as is standard in most high-performance dynamic language interpreters, we did kind of the simplest thing possible and implemented a CEK machine more or less directly. This has some nice advantages from the perspective of Racket, since the CEK machine by construction supports proper tail calls, and implementing callcc as required by the Racket standard is relatively straightforward. So that's the structure of the interpreter. It doesn't really tell us how to go to an efficient JIT compiler. And so we do that making use of a compilation technique known as tracing. The general strategy is to instrument your dispatch loop so that after each operation, you record into a buffer a sequence of instructions which emulates what the interpreter just did. When that buffer fills up, you ship that off to an optimizer and compiler, and you use the resulting code for subsequent iterations. And so you're effectively compiling specific paths through your control flow graph. And so that means the natural unit of compilation for a trace compiler becomes a loop. And so this is what the inner loop of our dot product examples looks like after we run it through the trace optimizer. We see there are a pair of guards which just ensure that we haven't run off the end of either of the arrays. If we haven't, we pull out the next value from each array, multiply those together, add that to the accumulator, and finally increment our two loop counters and jump back to the top for the next iteration. So we end up with a nice tight inner loop for our dot product function. So it's fairly obvious how to go from a trace to x86, but kind of at the beginning here, all we've done is really implement this very high-level interpreter. How do we go to actually tracing our racket code? And we do that using by shifting the burden of tracing one level up. So rather than tracing operations as performed by the source code of our language, we instead trace the operations as they're performed by the interpreter itself. This is known as meta tracing, and this is how the R Python JIT manages to be language agnostic. So now we've reduced the problem of tracing racket to observing what the interpreter does. We need to expose the right compilation unit, because otherwise we're just observing what this dispatch loop does. We don't really know what corresponds to a meaningful unit of compilation in racket. And this problem is known as loop finding. We have to find the loops in our racket source code so that we can actually compile them. So the standard way to go about this in a bytecode VM is to record cycles in your control flow graph. Generally, you find a hot program counter value, start recording, and you just step your program until you end up back at the hot program counter value that initiated tracing. And this is the default strategy in R Python, usually under the restriction that the program counter value you initiate tracing on is the target of backwards branches in your program. So it is just a location in your code that actually looks like the start of a loop. Unfortunately, the CEK machine doesn't really have a natural notion of a program counter. So as a rough proxy, we can take the AST location, since the CEK machine operates directly over AST nodes. So take, for example, this little program here. We have the myAdd function, which simply wraps addition, and the loop function, which sequentially calls myAdd twice, then recursively invokes itself back to the top. So since myAdd is invoked twice per iteration of loop, that red highlighted addition node there is going to be the hot AST node in our program. So we'll start tracing there. So we see we record the addition operation. We'll then return, or should back up and say, this is assuming we're already in the second invocation of myAdd here. So after recording the addition operation, we return into the body of loop. So we'll end up at the recursive call site. So we follow that back to the top, to the first invocation of myAdd, which we'll step into. And we finally get back to the addition node, which initiated tracing. So we've found what appears to be a loop. However, we haven't actually traced the whole body of what is the logical loop in our program, which is the entirety of this loop function. We would have instead wanted to follow this dotted path here. And unfortunately, since we're not compiling what is actually a loop in our racket source code, we're going to have to generate more traces, and we're not optimizing those traces as a single unit of compilation. So the resulting code will be significantly slower. And so we get around this using a construct we've been calling the call graph, which is really just a runtime representation of the call graph of our program. The intuition behind it is that racket's only looping construct is a tail recursive function. So we reduce the problem of finding loops in our program to one of detecting cycles in the call graph of the program. So this is what the resulting call graph for the previous example looks like. And so we just build the call graph during execution, since we're already observing what the program is doing. And when we detect a cycle in the call graph, we mark one of the participants as the start of a loop. In this case, it'll just be the loop function. And now we'll record the entire body of the loop function from beginning to end, optimizing it as a single compilation unit and producing nice tight code. So that gets us compiling the right kind of unit of code for our racket programs. How do we go about accomplishing this manual data specialization that we had to do for the second dot product example to actually get good code out of this? And the first thing we do is we specialize a lot of the internal interpreter data structures used inside of Picket. These are things like environments and continuation frames, which store fixed length, immutable arrays of racket level values. So that you end up with a lot of extra indirection, and since we represent floating point and fixed point values as boxed values, there's a lot of overhead for numeric computations. So instead, what we do is statically, when we compile Picket, we generate type-specialized versions specialized on the number of components and unbox the fixed length arrays into each, selecting the appropriate strategy at construction time. And additionally, any integer or floating point fields we further unbox into the body. So we're now storing our integers and floating point values in environments and continuations in an unboxed fashion, though the general representation is boxed. Similarly, we attempt to do the same thing for mutable racket level values, where we optimistically try to specialize containers like vectors and hash tables to use a contiguous unboxed representation when applicable. If we ever discover that some operation invalidates this assumption of homogeneity, we simply allocate a new strategy and storage and box everything back up and swap that out, which is an expensive operation, but it's one that occurs very infrequently in practice. So this ends up consistently being a win in performance. So what kind of performance results do we get out of doing all this? So first, some overall performance results. We have the Larceny benchmark suite, which contains about 50 scheme programs. It's a pretty standard benchmark suite that runs across a bunch of different scheme implementations. So we compare against Racket and also 3 optimizing ahead of time compilers, Larceny, Gambit, and Bigloo. We see Racket is the slowest when we take the geometric mean across all 50 benchmarks. The 3 optimizing compilers get successively faster, and Picket ends up being the fastest with a mean runtime about twice as fast as Racket. Similarly, we took the Racket entries for the computer language shootout benchmarks. These are notable because they've been kind of hand-tuned and specialized like the second dot product example. So these are ones where Racket should do pretty well on. And yet, again, Picket still ends up being about twice as fast in terms of overall performance. And since those shootout benchmarks have been manually specialized, we can use those to get an idea of how dependent Picket is upon this manual specialization process. So what we did is we took a couple of those benchmarks and manually despecialized them, inserting more generic polymorphic operations in place of all of our arithmetic and array operations. And we see when we run that through those kind of slowed down versions through Racket, we take about a 30% performance hit. Whereas under Picket, we only lose about 6% performance. And since we're already twice as fast as Racket was, it's safe to conclude that Picket is also significantly less dependent upon this manual specialization process to achieve reasonable performance. And finally, a bit about contracts. Since one of our goals is to eliminate the overhead of contracts, Racket implements its contract library using a feature known as impersonators and chaperones. These are data structures that allow you to wrap Racket-level values and attach callbacks which enforce the various user-level contracts. So you have overhead not just in enforcing the contract, but also in the extra cost for indirection to get to all of your data again. And this overhead ends up being quite significant. So this benchmark takes some of the original benchmarks from the paper describing the chaperones and impersonators, and we take those benchmarks and add and compare both systems with and without contracts on them to see how much adding contracts slows down the overall runtime. So the first 3 benchmarks, Bubble, Church, and Struct, are relatively small micro benchmarks. The final 2, ODE and Binomial, are larger. They're an ODE solver and a binomial heap tested on some image processing data. And we see across the board, Racket takes a pretty significant hit on all of them except for the ODE benchmark, whereas Picket for 3, Bubble, Struct, and ODE have slowdown factors pretty close to 1, and the Struct benchmark is, in fact, as fast as it was without contracts. So at least in many cases, we can significantly reduce and sometimes eliminate the overhead of contracts as well. And so kind of in summary, These dynamic language JIT compilation techniques are very effective for functional languages as well, even though they haven't been applied that much to functional languages, assuming you can provide the right unit of compilation and give it enough information to overcome the overhead of contracts and the need for manual specialization. Thank you.
I constructed the CEK machine explicitly as a proof construct, not as an abstract machine. I'm surprised to see it useful. I'm very surprised because it has an AST, not a flat instruction sequence.
Right.
Would you have, if you had a machine that has a flat instruction sequence, would you have done better with your looping optimizations? Loop finding.
Sorry. With our timings, it's hard to say. So
loop findings.
With loop findings.
I'm referring back to the talk where you say, I have to find loops, and you have explicitly acknowledged that there are problems with the CEK machine. Not surprising, it uses an AST, not an instruction sequence.
Right.
Would you find loops more easily if you had taken something like the SSD machine, added tail call behavior to it, and then looked for loops in the S part of the machine?
Right. So there's actually been a lot of work on various loop finding techniques to get better traces. In general, I don't think taking a flat representation would really improve the loop finding story very much. Certainly you can, so the original tracing system was actually designed to work on the flat assembly code, so presumably that's what you would get out if you just ran this through the compiler, the goal being to optimize your program binary. It still runs into this problem of detecting these false loops after you've kind of flattened your whole program into assembly language, because you end up with these weird false loops where either a call or a return ends up as a back edge in your program, regardless of whether it actually encodes a loop.
I expect Racket to be evolving relatively fast in Pycket as well. And like in 5 years from now, will the implementation still work? Do you plan to maintain it? Does the scheme community plan to maintain Pycket?
I don't know what plans the scheme community has to develop Picket. I'm not sure they would be interested in maintaining a scheme implementation in Python. But it's certainly an interesting test bed. I don't know about the long-term feasibility of replacing the current Racket implementation.
How much of Racket does Picket support?
So there are certain things we definitely don't support well. Things like the FFI are particularly hard to implement. That said, we support enough of Racket to support its whole contract system, typed Racket. Racket comes with about 1,500 built-in primitive operations, of which we support about 900. So we support enough to run most everyday Racket programs.
Historically, tracing just-in-time compilers have had a problem with algorithms which don't always have the same paths, and which operating instructions aren't always the same size. For example, quicksort and merge sort are classic examples. Have you done any benchmarks to show whether Pycket still has problems with these common of real-world situations? Or
Yes. So there are certainly well-known bad cases for tracing JIT compilation, and Picket will run afoul of those sometimes as well. That's not obvious on the benchmarks because we've reduced everything to geometric means, but there are definitely outliers where there's heavily branchy control flow, where Picket will be 2.5 times slower than a competitor when it doesn't map nicely onto the trace compilation kind of best case.
Is there any active research to work on that, or is that still an open problem?
There is some work on that I believe in the context of Lua JIT, attempting to kind of merge long common tails for traces to get back something closer to what would be produced by a standard compiler.
Thank you, Ernest.
Thank you.